Good day, sir. This is Group 1. I'm Wei Ying with metric number 271410. Today, I'm going to introduce my group members, topic, and the contents. My group members who involved in this topic is Safalas with metric number 258173, Ong Jia Yee 269674, Maizatul Athirah 273206, and Farhanah Izyan with metric number 273772. And our topic is Newton's laws of cooling. And the content are introduction, Newton's laws of cooling, the example, and the conclusion. I'll pass to the next to continue the introduction.
Hello, my name is Taufik Safalas. I will present how to apply ordinary differential equation or ODE in real life. Before that, we must know what is ODE. ODE is a differential equation containing one or more function of one independent variable and the derivative of those functions. ODE have been applied in many fields such as physics, electronic engineering, and population dynamics. For example, Newton law of cooling. What is Newton law of cooling? Newton law of cooling is the temperature of body change at the rate proportional to the difference in temperature between the body and surrounding. How to solve Newton of cooling? We can solve Newton of cooling use application of first order differential equation with method separate variable, homogeneous, and Bernoulli equation. That's all for me.
Okay, now I will explain about Newton's law of cooling. What is Newton's law of cooling? Newton's law of cooling is when the rate of loss of heat from our body is directly proportional to the difference in the temperature of the body itself and its surrounding. In this Newton's law of cooling, we use the formula dt over dt equal to k in bracket T minus Ts. From the formula, we get T is for the temperature of the object, Ts is temperature of the surrounding, while K is the constant. So to understand this concept, if the object is much hotter than its surrounding, T minus To will be large and positive, while dt over dt will be large and negative. So the object will cool quickly. However, if the object is a little hotter than its surrounding, then T minus To will be small positive and the object will cool slowly. Okay, now I will explain about limitation of Newton's law of cooling. Why Newton's law of cooling cannot be used in all situations? This is because to use Newton's law of cooling, firstly, the difference in temperature between the body and the surrounding must be small. And next, the loss of heat from the body must be by radiation only. And the most important thing in Newton's law of cooling is that the temperature of surrounding must remain constant during the cooling of the body. So if these 3 points are there, then we can use Newton's law of cooling. So there are many ways Newton's law of cooling have been used in real life situation. So firstly, in forensic science, in forensic they are really crucial to know the victim death time. So to calculate victim death time using Newton's law of cooling, they will take the dead body temperature and the crime scene temperature to know the exact victim death time. Okay, next, to measure the temperature of a heated meal, Newton's law of cooling are used to measure the time taken for the meter to cool down. Okay.
Hi, I'm Ong Jia Yee 269674. Now it's my turn to explain about the example in the Newton's law of cooling. An ice cube tray was found by Jane on the table. She measured the ice cube tray temperature 10 degrees Celsius at 10 am. The temperature of the ice cube tray became 15 degrees Celsius after 1 hour. And she noticed that the surrounding temperature was maintained at a constant temperature of 25 degrees Celsius. Assume that the ice cube tray is 0 degrees Celsius when it was taken out from the refrigerator. She wondered when was the ice cube tray had been taken out. Let's assume that capital T equal to temperature, lowercase t equal to time, and K equal to constant of cooling or heating. According to the Newton's law, the time rate of change of temperature is proportional to the temperature difference. The value of K is positive because it is a heating process, means the ice cube tray is absorbed heat. The temperature of the surrounding is always a constant, which is 25 degrees Celsius. Hence, we will get the general equation of d capital T divided by v lowercase t equal to K bracket capital T minus 25. To solve for the general solution of the above equation, we have to rearrange the equation by move all the capital T term one side and others one side. After rearrange, we found that the equation is in the general form of separable differential equation. Next, we integrate both sides of the equation. We will get ln capital T minus 25 equal to Kt plus C to get rid of the log by taking exponential of both sides. Then we will get capital T minus 25 equal to exponential power to Kt times exponential power to C. By replace e power to c with m, we will get the general equation of t equal to 25 plus n exponential power to kt. To solve the values of m and k, we first substitute small t with 0 and T0 equal to 10, which is the first measured temperature in the general equation. Then we will get m equal to negative 15. From the equation, we know that the ice cube tray becomes 15 degrees Celsius after 1 hour. Let's define our function to represent time in hours. So T1 equal to 15, and substitute it in the new general equation which replace m equal to negative 15. We will get k equal to negative 0.4055. Therefore, by replacing the k values, the general equation will become t equal to 25 minus 15 exponential power to negative 0.4055t. As we know that the ice cube tray is 0 degrees Celsius when it was taken out from the refrigerator. Then we substitute t equal to 0 into the general equation to find the time that ice cube tray had been taken out. After calculation, we find that t equal to negative 1.26 hours, which means the ice cube tray is taken out from refrigerator 1 hour, 15 minutes and 36 seconds before discovered by Jane. That's all from me. Thank you. I will pass to the next presenter.
We have shown and explained about our understanding of the ODE and how it is applicable to the real life problem. So the basic in solving the ODE is that we need to be able to do integration. However, it is much more complicated than the simple integration itself, as it involves us to determine the type of integration to use when solving the problems. We can conclude that DE are closely associated with the physical application, and it is also can be formulated into DE from various fields of science. Hence, many problems that are derived from the various fields can be described in DE, and by the manipulation of it can lead us to solving the problems. As a conclusion, the study of ODE is necessary to help in solving problems in many fundamental fields such as engineering, physics, and economics.